Continuing on with class number 20, here are some examples out of Cengel. So we have a rigid tank that contains 5 kilograms of R134A. It's initially at 20 degrees Celsius, 140 kilopascals. The refrigerant is now cooled while being stirred until its pressure drops to 100 kilopascals. We want to determine the entropy change of the refrigerant during this process. So let's switch over to here and see what's going on. Let's draw a little thing. All right, so it's being stirred. That means work is being placed into this thing. And it's also being cooled, right? So we have work coming in, and we have heat going out. So we also know that the mass is 5 kilograms, and we're trying to find the entropy change during here. So find delta S. State 1, we're given 2 pieces of information. We're not 100% sure. It says it's this refrigerant. We don't know if it's liquid or gas. So let's just look it up. All right, so this is going to be state 1 that we want to try to take a look at. And there's a refrigerant right here. It's 134. So I'm on 410 here. I'm going to go 134. That's ammonia. I think I went too far. Or maybe there's carbon dioxide. 410. Okay, so 134 is after 410. Why don't they put them in order? No, I don't know. Who knows? So this is, we said it was 20 degrees. Oh, and I decided to change this to 150. So that's me going, I think our life would be easier if it was 150 degrees. So starting out at 150. So let's take a look at 20. You can see that the saturation pressure is 572. So this is obviously the pressure is lower at this temperature, so we are going to be superheated. So let's switch over, and that's why I went to, instead of 140, I went to 150, because then I didn't have to interpolate. So I just changed the problem because I didn't give a shit. I didn't care, excuse me. So 20 degrees at 150. So let's see, what do we need to write down? I think, I might want to go, somebody might ask me how much heat, but it's, okay, so it's not an isothermal process. It is, in fact, an isometric process because it's the same volume. So we can't really use the change in entropy to find the change in heat, unfortunately. We could use maybe the change in internal energy. Maybe we could find yeah, that doesn't help us with, oh wait a minute, we can have so if there's no, yeah, if there's no work, well, we know there is work being done. The work and the heat are going to eat. It's hard to do. It's hard to say. It's not an isometric process, but we are putting the pressure does have to change. All right. Anyway, let's take a look at what we can do. We can find the volume if we wanted to, but I don't think we need to. All we need is no, we do need the volume, right? We do need the volume just in case. So we'll take out the specific volume and the entropy right here. So it's state 1, T, and let's see. Let's change this up. That's 150 to make our lives easier. State 1 at T1 equals 20 degrees Celsius and P1 150 kPa. We'll have the V, specific volume, is going to be 0.15405 cubic meters per kilogram. Let's see, I'll double check that. Yeah, and then the specific, or the enthalpy, well, I can say specific enthalpy, 18515. So S1 is equal to 1.8515 kilojoules per kilogram degree Kelvin. And do I need anything else? I don't think I decided I needed anything else. No, okay. And so what's going to happen after we do this? So we're now going to drop to at state 2. We'll remember that we have the V2 is going to equal to V2 because the mass hasn't changed and the volume hasn't changed. So at state 2, we have T at T, pressure. So this is going to be a little bit, oh, you know what I decided to do? I also changed this just to make my life easier. This is 101.3. P2 is equal to 101.3 kilopascals. All right, so we don't have an isothermal. So we can't really do anything with the Q because for one thing, the temperature and the entropy are changing as we're going from one state to one state to another state. But what we can do is look up at this and see if V is between the two. And we're hoping it is because otherwise we don't have enough information, I don't think. So we come to here and we find out that right there, it's because the reason why I changed it from 100 is because I didn't want to interpolate in between here. So we now know what the temperature is. It's going to be negative 26.3 if our, let's see, what was the number? The number was 0.15405. Yep, 0.15 is in between that VG and that VF. Therefore, we are a mixture, and we can find out what the quality of those are. So what we found out was VF is 0.0130728, and VFG is going to be 0.1894. So we're going to take 0.15403 because we're going to take this and set it equal to X VFG. So I should write the equation above it. I'm going to set the fluid 30728 plus X, and this will be state, the quality at state 2 times 0.1894. Find out what this is, and we'll go ahead and take my word for it that it's 81%. And then we can go and use that with the entropy because that's the thing we're trying to find. That's our find. So we can take and say that the SF, look that up in here, at 101.3. We can find the SF is 0.8690 and the SFG is 0.8763. Write that down. 0.8690 kilojoules per kilogram. SFG 0.8763. And so we'll find the S at state 2, taking the fluid and adding to it the quality times the difference here between the fluid and the gas, and 1.5788 kilojoules per kilogram degree Kelvin. So we can find out that delta S, big S, M times S2 minus S1. So they told us it was 5 kilograms. And our second state is 1.5788. Our initial state is negative 1.8515. So we're going to end up with a negative value of 1.364. And because it's a capital S, it's going to be kilojoules per degree Kelvin. Right? There's no kilograms in there. We already multiplied, right? So it's not small s. So it's decreasing during this process. So decreasing, but that's okay because only the S gen, the entropy generation. All right, so this actually comes back later in the section and talks about how the entropy generation has to be the thing that always increases. So we'll see that we're going to have an entropy that's going to be it's going to be reduced to this because the total heat of the environment has not been decreased, only into the this control volume has it been decreased. But this is a sign that energy is leaving, right? That heat is leaving from the process. And once again, I can't quantify from this things that shouldn't be true. I'm trying to think about other things that we've done. It's because it's a mixture, it kind of complicates things. We'll talk about that soon. Anyway.